The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so finally we get to positive definite matrices. I've used the word and now it's time to pin it down. And so this would be my thank you for staying with us while we do this important preliminary stuff about linear algebra. So starting the next lecture, we'll really make a big start on engineering applications. But these matrices are going to be the key to everything. And I'll call these matrices K. And positive definite, I will only use that word about a symmetric matrix. So the matrix is already symmetric, and that means it has real eigenvalues and many other important properties, orthogonal eigenvectors. And now we're asking for more. And it's that extra bit that is terrific in all kinds of applications. Right. So if I can do this bit of linear algebra. So what's coming then? My review session this afternoon at 4. I'm very happy that we've got, I think, the best MATLAB problem ever invented in 18085 anyway. So that should get onto the website probably by tomorrow. And Peter Buchak is like the MATLAB person. So his review sessions are Friday at noon. And I just saw him and suggested Friday at noon. He might as well just stay in here. And knowing that that isn't maybe a good hour for everybody, so you could see him also outside of that hour. But that's the hour he will be ready for all kinds of questions about MATLAB or about the homeworks. Actually, you'll be probably thinking more about also about the homework questions on this topic. Ready for positive definite? Okay. So yes, you said yes, right? All right. Okay. And you have a hint about these things. So we have a symmetric matrix, and the beauty is that it brings together all of linear algebra, including elimination. That's when we see pivots, including determinants, which are closely related to the pivots. And what do I mean by upper left? I mean that if I have a 3x3 symmetric matrix, and I want to test it for positive definite, and I guess actually this would be the easiest test if I had like a tiny matrix 3x3 and I had numbers, then this would be a good test. The determinants, by upper left determinants, I mean that 1x1 determinant. So just that first number has to be positive. Then the 2x2 determinant, that times that minus that times that has to be positive. Oh, I've already, in saying that, let me just put in some letters here. So A has to be positive. This is symmetric. So A times C has to be bigger than B squared. So that will tell us. And then for 2x2, we finished. For 3x3, we would also require the 3x3 determinant to be positive. But already here, you're seeing one point about a positive definite matrix. Its diagonal will have to be positive. And somehow its diagonal has to be not just above 0, but somehow it has to defeat B squared. So it has the diagonal has to be somehow more positive than whatever negative stuff might come from off the diagonal. That's why I would need A times C greater than B squared. So both of those will be positive, and their product has to be bigger than the other guy. Okay. And then finally, a third test is that all the eigenvalues are positive. And of course, if I give you a 3 by 3 matrix, that's probably not the easiest test, since you'd have to find the eigenvalues. Much easier to find the determinants or the pivots. Actually, just while I'm at it, I don't know if, so the first pivot, of course, is A itself. No difficulty there. The second pivot turns out to be the ratio of AC minus B squared to A. So the second, the connection between pivots and determinants is just really close. Pivots are ratios of determinants. If you work it out, the second pivot, maybe I would call that D2, is the ratio of AC minus B squared over A. In other words, it's C minus B squared over A. So that'll be positive when determinants are positive and vice versa. But then it's fantastic that the eigenvalues come into the picture. Okay, so those are three ways, three important properties of a positive definite matrix. But I'd like to make the definition something different. I'd like to, now I'm coming to the meaning. If I think of those as the test, that's done. Now the meaning of positive definite. Okay. And positive, the meaning of positive definite and the applications are closely related to looking for a minimum. And so what I'm going to bring in here, so it's symmetric. Now, for symmetric matrix, I want to introduce the energy. So that's why this is the reason why it has so many applications and such important physical meaning, is that what I'm about to introduce, which is a function of x, and here it is. It's x transpose times A, oh, K, not A. I'm sticking with K for my matrix, times x. I think of that as some f of x. Okay. And let's just see what it would be if the matrix was 2 by 2. A, B, B, C. Okay. Suppose that's my matrix. Okay, let's we want to get a handle on this is the first time I've ever written something that had x's times x's. So it's going to be quadratic. They're going to be x's times x's. So and x is a general vector of the right size, so it's got components x1, x2, and there it's transposed, so it's a row. And now I put in the A, B, B, C, and then I put in x again. Okay, this is going to give me a very nice, simple, important expression depending on x1 and x2. Now, can we do that multiplication? Maybe above I'll do the multiplication of this pair, and then I have the other guy to bring in. So here that would be ax1 plus bx2, and this would be bx1 plus cx2. So that's the first. That's this times this, and now I have to take, what am I going to get? What shape, what size is this result going to be? This k is n by n. X is a column vector, n by 1. X transpose, what's the shape of X transpose? 1 by n. So what's the total result? 1 by 1, just a number, just a function. It's a number. But it depends on the x's and the matrix inside. Okay, can we do it now? So I've got this to multiply by this. So do you see an x1 squared showing up? Yes, from there times there. And what's it multiplied by? The A. The first term is this times the ax1 is ax1 squared. So that's our first quadratic. Okay, now there'll be an x1, x2. Let me leave that for a minute and find the x2 squared, because it's easy. So where am I going to get x2 squared? I'm going to get that from x2, second guy here, times second guy here. There's a cx2 squared. So you're seeing already where the diagonal shows up. The diagonal A, C, whatever, is multiplying the perfect squares. And it'll be the off diagonal that multiplies the x1, x2. We might call those the cross terms. And what do we get for that then? We have x1 times this guy. So that's a cross term, b x1, x2, right? And here's another one coming from x2 times this guy. And what's that one? It's also b x1, x2. So x1 multiplied that, x2 multiplied that. And so what do we have for this cross term here? Two of them. 2b x1, x2. In other words, that b and that b came together in the 2b x1, x2. So here's my energy. Can I just loosely call it energy, and then as we get to applications, we'll see why. Okay, so I'm interested in that because it has important meaning. And so now I'm ready to define positive definite matrices. So I'll call that number 4, but I'm going to give it a big star, even more, because it's the sort of key. So the test will be, you can probably guess it. I look at this expression, that x transpose AX, and if it's a positive definite matrix and this represents energy, the key will be that this should be positive. This should be positive for all x's. Well, with one exception, of course. All x's except which vector is it? X equals 0 would just give me, I see how you put k. It's my default for a matrix, but should be it's k. Okay, except x equals 0, except the 0 vector. Of course, if x1 and x2 are both 0. So, okay. Now that looks a little maybe less straightforward, I would say, because it's a statement about this is true for all x1 and x2. For all, and we better do some examples and draw a picture. Let me draw a picture right away. Suppose, so here's x1 direction, here's x2 direction, and here's the x transpose AX, my function. Okay, this is in 3, so this depends on 2 variables, and so it's going to be a sort of a surface if I draw it. Now, what point do we absolutely know? And I put A again. I am so sorry. Okay. Okay. So, well, we know one point that's there, whatever that matrix might be. It's there, 0, right? You just told me that if both x's are 0, then we automatically get 0. Now, what do you think the shape of this curve, the shape of this graph, this is going to look like? The point is, if we're positive definite now, so I'm drawing the picture for positive definite. My definition is that the energy goes up. It's positive, right? When I move away from that point, I go upwards. That point will be a minimum. And any guess, let me just draw it roughly. So, here I am. So it sort of goes up like this. Kind of, yeah, does that, I don't know what, these cheap 2D boards, and I've got a 3-dimensional picture here. But, but you see it somehow. What word or what's your visualization? Sort of, it has a minimum there. That's why minimization, which was like the core problem in calculus, is here now. But for functions of for functions of 2x's or n x's. We're up the dimension over the basic minimum problem of calculus. Okay, so I think, yeah, it's sort of like a parabola. Its cross sections cutting down through the thing would be just parabolas because of the x squared. I'm going to call this a bowl. It's a short word for, so do you see it? It opens up. That's the key point, that it opens upward. And let's do some examples. Tell me some positive definite. So positive definite, and then let me here put some not positive definite cases. Okay, tell me a matrix. Well, what's the easiest first matrix that occurs to you as a positive definite matrix? The identity. Okay, that passes all our tests. Its eigenvalues are 1, its pivots are 1, the determinants are 1, and the function is x1 squared plus x2 squared with no b in it, and it just, you know, it's just a perfect bowl, perfectly symmetric, the way it would come off a potter's wheel. Okay, now let me take one that's maybe not so. Let me put a 9 there. So I'm off to a reasonable start. I have an x1 squared and a 9x2 squared. And now I want to ask you, what could I put in there that would leave it positive definite? Well, give me a couple of possibilities. What's a nice, not too big now, that's the thing. 2. 2 would be fine. So if I had a 2 there and a 2 there, I would have a 4 x1, x2, and it would, like this, instead of being a circle, which it was for the identity, the level plane there would cut out an ellipse instead. But it would be a good ellipse. So that's because we're doing squares. The Greeks understood these second degree things, and they would have known this would have been an ellipse. Okay. How high can I go with that 2, or where do I have to stop? Where would I have to, if I wanted to change the 2, let me just focus on that one. Suppose I wanted to change it. First of all, give me one that's, how about the borderline? 3 would be the borderline, right? Why is that? Because at 3, we have 9 minus 9 for the determinant. So the determinant is 0. Of course, it passed the first test. 1 by 1 was okay, but 2 by 2 was at the borderline. And let's see, what else should I think? Oh, okay, that's a very interesting case, the borderline. It almost makes it, but what are the can you tell me the eigenvalues of that matrix? Don't do any quadratic equations. How do I know, what's one eigenvalue of a matrix? You made it singular, right? You made that matrix singular, determinant 0. So one of its eigenvalues is 0, and the other one is visible by looking at the trace. I just quickly mentioned that if I add the diagonal, I get the same answer as if I add the 2 eigenvalues. So that other eigenvalue must be 10. And this is entirely typical, that 10 and 0, the extreme eigenvalues, lambda max and lambda min, are bigger than, these diagonal guys are inside. They're inside, between 0 and 10. And it's these terms that enter somehow and gave us an eigenvalue of 10 and an eigenvalue of 0. I guess I'm tempted to try to draw that figure, just to get a feeling of what's with that one. It's always helps to get the borderline case. So what's with this one? Let me see what my quadratic would be. Can I just change it up here rather than rewriting it? So I'll put it up here. So I have to change that 4 to what? For now that I'm looking at this matrix. That 4 is now a 6. 6. Okay, this is my guy for this one, which is not positive definite. Let me tell you right away the word that I would use for this one. I would call it positive semi-definite, because it's almost there, but not quite. So semi-definite allows the matrix to be singular. So semi-definite, maybe I'll do in green what semi-definite would be. Semi-def would be eigenvalues greater than or equal 0. Determinants greater than or equal 0. Pivots greater than 0 if they're there, or then we run out of pivots. You could say greater than or equal to 0 then. And energy greater than or equal to 0 for semi-definite. And when would the energy, what x's, what would be the, like you could say the ground states or something, what x's, so greater than or equal to 0, and emphasize that possibility of equal in the semi-definite case, when would this, suppose I have a semi-definite matrix. Yeah, I've got one. But it's singular. So that means a singular matrix takes some vector x to 0, right? For if my matrix is actually singular, then there will be an x where kx is 0. And then, of course, multiplying by x transpose, I'm still at 0. So the x's, the zero energy guys, this is straightforward. The zero energy guys, the ones where x transpose kx is 0, would be states, will happen when, this will happen when kx is 0. If kx is 0, and we'll see it in that example. We'll see it in that, let's see it in that example. What's the x for which is, I could say, in the null space? What's the vector x that matrix kills? 3 minus 1, right? 3 times, the vector of 3 minus 1, 3 minus 1 gives me 0, 0. That's the vector that, so I get 3 minus 3, the 0, 9 minus 9, the 0. So I believe that this thing will be, is it 0 at 3 minus 1? I think it has to be, right? If I take x1 to be 3 and x2 to be minus 1, I think I've got 0 energy here, do I? x1 squared will be the 9, and 9x2 squared will be 9 more. And what will be this 6x1, x2? What will that come out for this x1 and x2? Minus 18. Had to, right? So I'd get 9 from there, minus 18, 0. So the graph for this positive semi-definite will look a bit like this. There'll be a direction in which it doesn't climb. It doesn't go below the base, right? It's never negative. This is now the semi-definite picture. But it can run along the base. And it will, for the vector x1 equal 3, x2 equal minus 1, I don't know where that is, 1, 2, 3, and then maybe minus 1, along some line here, the graph doesn't go up. It's sitting, can you imagine that sitting in the base? I'm not Rembrandt here, but in the other direction, it goes up. Oh, the hell with that one. Do you see sort of, it's like a trough, would you say? I mean, it's like, a bit of a drain pipe or something. It's running along the ground where along this 3 minus 1 direction. And in the other directions, it does go up. So it's shaped like this, with the base not climbing. Whereas here, there's no bad direction, climbs every way you go. So that's positive definite, and that's positive semi-definite. Well, suppose I push it a little further. let me make a place here for a matrix that isn't even positive semi-definite. Now it's just going to go down somewhere. Tell me, I'll start again with 1 and 9 and tell me what to put in now. So this is going to be a case where the off diagonal is too big. It wins and prevents positive definite. So what number would you like here? 5? 5 is certainly plenty. Okay. So now I have 1, 5, 5, 9. Let me take a little space on a board just to show you. So, sorry about that. Okay. So I'm going to do the 1, 5, 5, 9, just because they're all important, but then we're coming back to positive definite. So if it's 1, 5, 5, 9, and I do the usual x transpose kx, and I do the multiplication out, I see the 1x1 squared, and I see the 9x2 squareds, and how many x1, x2s do I see? 5 from there, 5 from there, 10. And I believe that can be negative. The fact of having all nice plus signs is not going to help it, because we can choose, as we already did, x1 to be like a negative number and x2 to be a positive, and we can get this guy to be negative and make it, in this case, we can make it defeat these positive parts. Okay, what choice would do it? Let me take x1 to be -1 and tell me an x2 that's good enough to show that this thing is not positive definite or even semi-definite. It goes downhill. Take x2 equal, what do you say? 1/2? Yeah, I don't want too big an x2, because if I have too big an x2, then this will be important. Does 1/2 do it? So I've got 1/4, that's positive, but not very. 9/4, so I'm up to 10/4. But this guy is what? 10, and the minus is -5. Yeah, so that absolutely goes. At this one, I come out less than 0. And I might as well complete. So this is the case where I would call it indefinite. Indefinite. It goes up, like if x2 is 0, then it's just got x1 squared, that's up. If x1 is 0, it's only got x2 squared, that's up. But there are other directions where it goes downhill. So it goes either up, it goes both up in some ways and down in others. And what kind of a graph, what kind of a surface would I now have for x transpose, for this x transpose, this indefinite guy? So up in some ways and down in others. This gets really hard to draw. I believe that if you ride horses, you have an edge on visualizing this. So it's called, what kind of a point is it called? Saddle point. It's called a saddle point. So what's a saddle point? Is that, it's not bad, right? So this is a direction where it went up. This is a direction where it went down. And so it sort of fills in somehow. Yeah. Or maybe if you don't, I mean, who rides horses now? So actually, maybe something we do is drive over mountains, right? So the path, so that, right, if the road is sort of well chosen, the road will go, it'll look for this would be, yeah, here's our road. We would do as little climbing as possible. The mountain would go like this, sort of. So this would be like the bottom part looking along the peaks of the mountains, but it's the top part looking along the driving direction. So driving, it's a maximum, but in the mountain range direction, it's the minimum. So it's a saddle point. Okay. So that's what you get from a typical symmetric matrix. And if it was -5, it would still be the same saddle point. It would still be 9 minus 25. It would still be negative and a saddle. Okay. Positive guys are our thing. All right. So now back to positive definite. With these 4 tests and then the discussion of semi-definite. Okay. Very key, that energy. Let me just look ahead a moment. Most physical problems, many physical problems, you have an option. Either you solve some equations. Either you find the solution from our equations, Ku equal F, typically. Matrix equation or differential equation. Or there's the another option of minimizing some function, some energy. And it gives the same equations. So this minimizing energy will be a second way to describe the applications. Okay, now, can I get a number 5? There's an important number 5, and then you know really all you need to know about symmetric matrices. Oh, this gives me about positive definite matrices. This gives me a chance to recap so I'm going to put down a number 5. Because this is where the matrices come from. Really important, and it's where they'll come from in all these applications that Chapter 2 is going to be all about, that we're going to start. So they come, these positive definite matrices, so this is another way it's a test for positive definite matrices, and it's where they come from. So here's a positive definite matrix. If I take, they come from A transpose A. A fundamental message is that if I have just an average matrix, possibly rectangular, could be square but not symmetric, then sooner or later, in fact, usually sooner, you end up looking at A transpose A. We've seen that already. And we already know that A transpose A is square. We already know it's symmetric. And now we're going to know that it's positive definite. So matrices like A transpose A are positive definite or possibly semi-definite. We have to, there's that possibility. If A was the 0 matrix, of course, we would just get the 0 matrix, which would be only semi-definite, or other ways to get a semi-definite. But, okay. So I'm saying that if I have a matrix, any matrix, and I form A transpose A, I get a positive definite matrix, or maybe just semi-definite, but not indefinite. Can we see why? Why? So why is this positive definite or semi? So that's my question. And the answer is really it's just neat and worth seeing. So do I want to look at the pivots of A transpose A? No. There's something, but whatever they are, but I can't really follow those well, or the eigenvalues very well, or the determinants. None of those come out nicely. But the real guy works perfectly. So look at X transpose KX. So I'm just doing following my instinct here. So if K is A transpose A, my claim is, what am I saying then about this energy? What is it that I want to discover and understand? Why it's positive. Why does taking any matrix, multiplying by its transpose, produce something that's positive? You know, in some way this is, yeah. Can you see any reason why that quantity, which looks kind of messy, I just want to look at it the right way to see why that should be positive, that should come out positive. So I'm not going to get into numbers. I'm not going to get into diagonals and off diagonals. I'm just going to do one thing to understand that particular combination, X transpose A transpose AX. What shall I do? Anybody see what I might do? You're seeing here, if you look at it again, what are you seeing here? Tell me again. If I take AX together, then what's the other half? It's the transpose of AX. So I just want to write that as, I just want to think of it that way, as AX, and here's the transpose of AX, right? Because transposes of AX, the transpose goes in the opposite order, and the multiplication, this is the great, I call these a proof by parenthesis, because I'm just putting parentheses in the right place, but I'm not, that's the key law of matrix multiplication is that I can put AB times C is the same as A times BC. That rule, which is just multiply it out, and you see that parentheses are not needed, because if you keep them in the right order, you can do this first, or you can do this first. Same answer. Okay, what do I learn from that? What was the point? This is some vector, I don't know especially what it is, times its transpose. So that's the length squared. What's the key fact about that? That it is never negative. It's always greater than 0 or possibly equal. So when it's equal 0 when does that quantity equal 0? When AX is 0. When AX is 0. Because this is a vector. That's the same vector transpose, and everybody's got that picture. When I take any y transpose y, I get y1 squared plus y2 squared plus through yn squared, and I get a positive answer except if the vector is 0. So it's 0 when AX is 0. Okay. So that's going to be the key. If I pick any matrix A, and I can just take an example, but the applications are just going to be full of examples where the problem begins with a matrix A, and then A transpose shows up, and it's the combination A transpose A that we work with, and this we're just learning that it's positive definite, unless, okay, so shall I just hang on since I've got here? I have to say, when is it, I have to get these two possibilities, positive definite or only semi-definite. So what's the key to that borderline question? This thing will be only semi-definite if there's a solution to AX equals 0, right? If there's a solution to, if there is an X, well, there's always the 0 vector. The 0 vector, I can't expect to be positive. So I'm looking for, if there's an X so that AX is 0, but X is not 0. So then I'll only be semi-definite. So I'll only be that's the test. If there's a solution to AX equals 0. When we see applications, that'll mean there's a displacement with no stretching. You know, we might have a line of springs. And when could the line of springs displace with no stretching? When it's free, right? If I have a line of springs and no supports at the ends, then that would be the case where it could shift over by the 1, 1, 1 vector. So that would be the case where the matrix is only singular. We know that. The matrix is now positive semi-definite. We just learned that. So the free matrix, like B, both ends free, or C. So our answer is going to be that K and T are positive definite. And our other two guys, the singular ones, of course, just don't make it. B at both ends, the free line of springs, it can shift without stretching. Since AX will measure the stretching, when it just shifts, rigid motion, the AX is 0, and we see only positive definite. And also C, the circular one, there it can displace with no stretching because it can just turn in the circle. So these guys will be only positive semi-definite. Okay. That's so another, maybe I better say this another way. This is positive. When is this positive definite? Can I use just a different sentence to describe this possibility? This is positive definite provided. So what I'm going to write now is to remove this possibility and get positive definite. This is positive definite provided. Now, I could say it this way. The A has independent columns. So I just needed to give you another way of looking at this AX equals 0 question. If A has independent columns, what does that mean? That means that the only solution to AX equals 0 is the 0 solution. In other words, it means that this thing works perfectly and gives me positive when A has independent columns. Yeah, let's just remember our KTBC. So here's a matrix with, let me take T. Yeah, here's a matrix. So let me take the T matrix. That's this one, this guy, and then the third column is 0, -1, 2. Those three columns are independent. They point off. They don't lie in a plane. They point off in three different directions. And that's what, and then there are no solutions to, there are no x's that go kx equals 0. And there are no, so that would be a case of independent columns. Let me make a case of dependent columns. So I'm going to make it B now. Now, the columns of that matrix are dependent. There's a combination of them that gives 0. They all lie in the same plane. There's a solution to that matrix times x equals 0. What combination of those columns shows me that they are dependent? That some combination of those three columns, some amount of this plus some amount of this plus some amount of that column gives me the 0 vector. You see the combination. What should I take? 1, 1, 1 again. No surprise. That's the vector 1, 1, 1 that we know is in the everything shifting the same amount, nothing stretching. Yeah, okay. So, well, talking fast here about positive definite matrices. This is the key. Let's just ask a few questions about positive definite matrices as a way to practice. Suppose I have one. Positive definite. What about its inverse? Is that positive definite or not? Okay. So I've got a positive definite one. It's not singular. It's got positive eigenvalues, everything else. Its inverse will be symmetric, so I'm allowed to think about it. Will it be positive definite? What do you think? Well, you've got a whole bunch of tests to sort of mentally run through. Pivots of the inverse, you don't want to touch that stuff. Determinants, no. What about eigenvalues? What would be the eigenvalues? If I have this positive definite symmetric matrix, its eigenvalues are 1, 4, 5. What can you tell me about the eigenvalues of the inverse matrix? They're the inverses, so those three eigenvalues are 1, 1/4, 1/5. What's the conclusion here? It is positive definite. Those are all positive. It is positive definite. So if I invert a positive definite matrix, I'm still positive definite, and all the tests would have to pass. It's just I'm looking each time for the easiest test. Okay, let me look now for the easiest test on K1 plus K2. Suppose that's positive definite and that's positive definite. What if I add them? What do you think? Well, we hope so, but we have to say which of my 1, 2, 3, 4, 5 would be a good way to see it. Would be a good way to see it. Good question. 4? Yeah, we certainly don't want to touch pivots, and now we don't want to touch eigenvalues either. Of course, if number 4 works, others will also work. The eigenvalues will come out positive, but not too easy to say what they are. Let's try test number 4. So K1, what's the test? So test number 4 tells us that this part, X transpose K1X, that part is positive, right? That part is positive. If we know that's positive definite. Now about K2, we also know that for every X, you see it's for every X, that helps. Don't let me put X2 there. For every X, this will be positive. And now what's the step I want to take? To get some information on the matrix K1 plus K2? I should add. If I add these guys, you see that then I can write that this way. And what have I learned? I've learned that that's positive, even greater than, except for the 0 vector. Because this was greater than, this is greater than. If I add 2 positive numbers, the energies are positive and the energies just add. The energies just add. So that definition 4 was the good way, just nice, easy way to see that if I have a couple of positive definite matrices, a couple of positive energies, I'm really coupling the 2 systems. You know, this is associated somehow. I've got 2 systems, I'm putting them together, and the energy is just even more positive. You know, it's more positive than either of these guys because I'm adding. Yeah. As I speaking here, will you allow me to try test number 5, this A transpose A business? Suppose K1 was A transpose A. If it's positive definite, it will be. And suppose K2 is B transpose B. If it's positive definite, it will be. Now I would like to write the sum somehow as, in a way, in this something transpose something. And I just do it now because I think it's like you won't have thought of this, perhaps have thought of this way to do it. let me watch. Suppose I create the matrix AB. That'll be my new matrix. They call it C. Am I allowed to do that? I mean, that creates a matrix. These A and B, they had the same number of columns, n, so I can put one over the other, and I still have something with n columns. So that's my new matrix C, and now I want C transpose. By the way, I'd call that a block matrix. You know, instead of numbers, it's got 2 blocks in there. Block matrices are really handy. Now, what's the transpose of that block matrix? You just like have faith. Just have faith with blocks. It's just like numbers. If I had a matrix 1, 5, then I'd get a row 1, 5. But now what do you think? Yeah, this is worth thinking about even after class. What would be, if this C matrix is this block A above B, what do you think for C transpose? A transpose, B transpose, side by side. Just put in numbers and you'd see it. And now I'm going to take C transpose times C, right? I'm calling it C now instead of A, because I've used the A in the first guy, and I've used B in the second one, and now I'm ready for C. So how do you multiply block matrices? Again, you just have faith. What do you think? Tell me the answer. A transpose, I multiply that by that, just as if they were numbers. And I add that times that, just as if they were numbers. And what do I have? I've got K1 plus K2. So I've written K1, this is K1 plus K2. And this is in my form C transpose C that I was looking for, that number 5 was looking for. So it's done it. It's done it. The fact of getting K1 in this form, K2 in this form, then I just made a block matrix and I got K1 plus K2. That you know, that's not a big deal in itself, but block matrices are really handy. It's good to take that step with matrices. Think of possibly the entries as coming in blocks and not just one at a time. Well, thank you. Okay, I swear Friday we'll start applications in all kinds of engineering problems, and you'll have new applications.